So welcome to part two of the recap for this last week's lectures. I'm just going to hit the highlights here. The main idea is that convergent sequences are bounded, and we want to show just that this technique in the proof is very common. It's used in a lot of cases, and especially as you move to more abstract spaces. You want to have co-convergent sequences are bounded, Cauchy sequences are bounded. There's all sorts of times where you want to say, hey, I want to get a bound because I don't care so much about like the limit of a sequence or something else. Like I just care about replacing the sequence with something that's larger in magnitude than like anything else in the sequence. And that came in the proof, for instance, of theorem 9.4. We saw that in proving the product limit of the product is the product of the limits. So the main idea is, look, if I have a convergent sequence, then for any kind of epsilon I pick, that creates some interval around the limit, and then eventually all the terms in the sequence have to get bounded after some n, right? There's some point where then all the terms are just bounded within this little interval. But those are most of the terms in a sequence because it's an infinite number of them, but you still have this finite number that's before the capital N in the number of terms. And you say, well, what do I deal with those terms? And you see some of them might be in that bound, but some of them, perhaps all of them, or most, or you don't know, are perhaps outside of that interval. And so then you say, okay, well, I have to do something about those. And you just say, well, that's a finite number, and a finite number of terms, and a finite number of real numbers clearly has a max and a min. And so that's like really the whole argument in some case. And we just say, look, I have a convergent sequence. I don't need to prove it. I'll pick an epsilon to be whatever I want. I might as well pick it to be something simple like 1. And that tells me that eventually all the terms are between s minus 1 and s plus 1. And because I don't know if the s is itself like positive or negative, s minus 1 might be larger in magnitude than s plus 1. So I end up taking the absolute values of them when I consider how to choose my bound. And then I just take the remaining terms that aren't within this bound, and I just take the magnitude of those as well, because some might be really large but negative. And so I take all the absolute value and I say, now I just have a finite set of numbers, and that has a max, and that's what I choose, and then it bounds everything. That's really the whole argument. The only other version of this that is something we didn't talk about in class because we didn't have time is in Lemma 9.5. Here we said if Sn converges to S, and if all the terms are not 0 and the limit's not 0, then 1 over Sn converges to 1 over S. And in order to do this, I went through this argument here that I have. I believe it's all written out in the notes for you. If not, I'll kind of scroll slowly on the screen so you can see it. But the point of this is, really about the proof. We follow the same type of argument that a convergent sequence is bounded. That's the thing to realize. So you really want to say, like, because I'm taking 1 over Sn and I want to show it converges to 1 over S, since the terms aren't 0 and they don't go to 0, I kind of want to make sure that terms aren't getting arbitrarily large. Because, like 1 over x, for instance, goes to infinity as x goes to 0. We're all familiar with kind of this plot of 1 over x like this. Well, we know that the limit that we're dealing with is not 0 and the terms aren't 0, so we shouldn't have that happen. And we prove that doesn't happen because it allows us to then go through the proof of theorem 9, or I suppose I should say Lemma 9.5. So I said theorem here, but I really think I mean Lemma 9.5. So the basic claim is, all right, this that we're proving. If S of n converges to S, the terms are all not 0 and the limit's not 0, then in fact the terms are bounded away from 0. Like there's some minimum number that's greater than 0 that's smaller than all of the terms that show up in the sequence. And this allows me to say that when I divide by the terms, then they can kind of be bounded above. So what do? I take epsilon to be half the distance from the limit term to 0, right? Because this is literally the distance between the limit and 0 is just that, which is S. And I'm saying, okay, so wherever S is, I look at its distance to 0 and I take half that distance. And that's a positive number because S was not 0. And so then you say, well, look, Sn converges to S, which means eventually, like it's this whole type of argument here, just formalized what eventually means, you can get the terms to be less than that this is playing the role of my epsilon, the 1/2 times absolute value of S. And you just do this rearrangement now. We're getting kind of to be experts at doing this. This is shown up in the homework, for instance, that was recently due. You say the Sn terms are now bounded between S minus 1/2 the absolute value and S plus 1/2 its absolute value. And then you just go through these cases. There's basically two cases. S is greater than 0, S is less than 0. Because S is not 0, it's got to be one of these two. If S is greater than 0, then S is its absolute value, right? Absolute value of a positive number is it. And so right away, that tells me that S minus 1/2 the absolute value of S is just actually equal to half of the absolute value, and that's greater than 0. And what does that tell me? The Sn terms are greater than 0 after some point. And so the Sn terms then are also then positive, so they're equal to their absolute value as well. That's what this is saying. And then if S is less than 0, then S is equal to the negative of the absolute value, right? Just check the signs, it's pretty clear. So, if I wanted to say that I have -3, that's equal to negative the absolute value of -3, right? -3. So something like that. And so then again, you work with this upper bound, and then you say, well, that means that eventually, after the capital N, all the Sn terms actually have to then be negative, which means they are equal to the negative of their absolute value. But then you play this game and say, well, that means that the Sn terms and absolute value are actually greater than 1/2 the absolute value of S. It's a little technical. It can kind of get confusing in your mind, but if you just put in numbers for this, you see, oh yeah, this has to be true. And then just look at how I choose the little m. It's just like before. I've basically now bounded from these two cases. I've shown the absolute value of Sn is greater than 1/2 the absolute value of S after some point. And I say, well, what about the original, the finite set of terms that happened before this capital N? And I just go, oh, well, I'll just throw the absolute values of those in there as well. And then because none of the terms were 0, that was in the assumption, none of the terms are 0, then this is a finite set of real numbers. It has a minimum, and it's a minimum of a set of terms that are all greater than 0. None of them are 0. So right away, then this is the lower bound, just like we had the upper bound. So, hopefully that makes sense. We can recap that if there's some question on Monday, but please, I'm hoping everyone's looking this over. They're following along. Drawing pictures and putting numbers in is useful for this. And then, I want you, I believe I actually mean lemma here. That's got to be lemma 9.5, because then proving 9.6 becomes quite trivial. So, all right. Thanks for listening, and I'll see you in class on Monday.